Hello everyone, this is Mr. Mullicash again. This is our week 12 video for Math 171 through Johnston Community College. If you're watching this video and you have any questions about what you see here, this is my email address. This week's video we're going to talk about what inverse functions are, and there's a lot to talk about with inverse functions. So I'll be as brief as I can. And then we'll move into what's called an exponential function and a specific application of that called compound interest. You're really going to be wanting to pay attention to compound interest if you ever want to borrow money or invest money. That's really important that you hear that part of the video. Okay, good. So what is an inverse function? Okay, well, think about what a function does. Whoops. A function takes an input usually called x. That's the domain variable. It does some set of operations, and then you get a range variable, right? So what we want to do with our inverse function is take the x and replace x with y and y with x, so that the output in this other function would be x and the input would be y. So in essence, we've inverted those two things, right? Okay, so this would be what a function does. Okay, what an inverse function does is it says, okay, well, if we ended with this, how would I get back to the beginning? How would I be able to take the end and go back to the beginning? And what we have to do is invert and do some inverse operations. And I'm sorry that my marker is real thick and it doesn't show up very well, but those are operations, and these are the inverse operations. And how you do the inverse operations have to be done in the reverse order that the standard operations were done. Okay, so let's look at an example. Let's say that we have a function that takes the input variable and multiplies it by 3 and then subtracts 6 from that. Okay, so there's two things that are done, right? You take x, right? You multiply it by 3, and then you subtract 6, and then you get your range variable, your y variable, right? So, okay, so this is our function. Okay, so our inverse function is going to have to start with x and do the opposite thing in the opposite order, right? So your x value is, first you're going to add 6. Now, why is this the first thing that I did? Because the last thing I did was subtract 6. So you're going to have to go backwards up the chart here and do the inverse operation. Okay, so your first thing you're going to do is add 6, and then what we're going to do is divide by 3, and then you get your new range variable. So this is called the inverse function, and you may not realize what I put up there. And again, I'm needing to write bigger, but that's f raised to the -1 of x. This is the way it's written, but I'd never read it again like that. That's read f inverse of x. Okay, so f inverse of x is, we start with x and we add 6, and then we take that entire quantity and divide it by 3. Okay, so those two things are called inverse functions. So that's, an example. Now, if this flowchart thing doesn't make sense to you, then here's another way of dealing with this. Okay, so keep in mind this is the answer that we're looking for. All right, so what I'll do is I'll make two sides of my paper here. I'll have my f of x and I have my f inverse of x. And for now, I'll change that f of x to y. You're probably used to doing that by now. Okay, so this is the input and y is the output. So over here, I'm going to change the x and y around so that the input would be there and the output would be what I started with. Okay, so what I have to do is I have to get y by itself over here, so to speak. I have to find out what y is in this equation. So if you think about it, the first thing I need to do to both sides is add 6. I need to get rid of the minus 6. I wouldn't divide by 3 before getting rid of that minus 6. I'd have to add 6 to both sides, right? So there you go. We get x plus 6 equals 3y, so that these 6's go away. And then the next thing I'd have to do is divide by 3, right? Okay, so now I knew my new output variable is the inverse function of x, right? So that means that the inverse function of x is where you take x and add 6 and divide it by 3. Okay. All right. Now, what I'd like to do on the back of this paper is to graph both of these things. And now, you can tell that these are both linear functions. This is the slope, this is the y-intercept. Here, I could write this as 1/3 x plus 6 divided by 3, which is 2. So that's the same thing, right? If you wrote this down on your paper, I would count it completely correct, as opposed to this. All right, so let's go graph both of these things on the back and see what they look like. Okay. And what I mean by the back is I have some graph paper. Great. Okay. So three x minus 6. Okay, let's do that first. So, y-intercept, negative 6, up 3 over 1. Right, so we can kind of map out some points here, and we can draw. I'm going to try my best to draw a straight line through these points. It's easier to draw a straight line if you have lots of points. So every time you go up 3, you go right 1. Okay, and so that's the f of x is 3x minus 6. Okay, so what was the other thing? It was 1/3 x plus 2, right? So here's the plus 2. And now the slope is up 1 over 3, right? Up 1 over 3, up 1 over 3, up 1 over 3. And I could go down 1 and left 3 because a negative divided by negative is also a positive slope, right? So, yeah, we can have lots of these little dots here that maps out a straight line. Okay, so this is our inverse function. F inverse of x is 1/3 x plus 2. All right, now there's something about the graph of an inverse function as opposed to its standard function. And the thing you need to know about this graphically is that the line y equals x, which goes through the origin and has slope 1, is a line of symmetry for this entire graph. So if you look at this, okay, and if you kind of turn your graph a little bit, so the line y equals x exactly cuts the graph in half. So one graph is reflected over the line y equals x to make the other one. This means if you're given a graph of a function, you can immediately graph the inverse by taking every point and reflecting it over this line. So this is what the inverses look like graphically, okay? Now, speaking of, let's just draw a random graph here. Let's just draw a random graph, okay? Like, say we have something like this, okay? So this is definitely a function, at least I meant for it to look like a function. There we go. Okay, so it passes the vertical line test. This is definitely a function. Every x has exactly one y for an output, right? So if I drew the line y equals x, what, and this is f of x, what would the graph of the inverse function look like? Well, I could try to draw it. You know, it would take a little bit of ingenuity here. I'm going to try to draw that. So something like this, and then it kind of goes, let's see, maybe like that. Yeah, something like that. All right, so this one right here is f inverse of x, right? And if you look at that graph, that is not a function. It doesn't pass the vertical line test, right? So the reason I'm mentioning that is because in order, let's write this down. In order for a function to be invertible, what do I mean by invertible? It means that you can do what I just tried to do, and the function's still at, the inverse is still a function. So for this to happen, for the other thing to work out to be a function, the original function must be 1 to 1. Okay, so 1 to 1 means every x has one y, oops, on y? That doesn't make sense. One y value, and every y has exactly one x value. Both of these things have to be true. 1 to 1. So that thing that I drew earlier, this mess right here, right? Every x does have one y, but there are some y values, for example, -1 here, that have 1, 2, 3 x values, right? So this is not a 1-to-1 function, right? This is a 3-to-1 function or something like that, or maybe, yeah, 3-to-1. So there's 3 different x values for that y value. So when I go to invert this thing, the horizontal line, it'll become a vertical one, and it won't be a function anymore. Okay, so that's pretty much what it means to be a 1-to-1 function. All right, so that's pretty much all we want to say right now about inverse functions. Now let's talk a little bit about exponential functions. And to give you an idea of what an exponential function is, we're going to talk about money to start with. Okay, so let's give you an example of what I'm talking about. Let's say that we have an extra $100 maybe we got for Christmas, and we don't know what to do with it. Of course, everybody knows what to do with it, but let's just say that we want to invest it, right? We want to invest it, okay? So we want to invest this at 5% interest per year, let's say for 5 years. And then at the end of the 5 years, we'll see how much money we have, right? So you can pretty much easily know that 5% of 100 is 5. So you're going to get $5 in interest every year if we do what's called simple interest. Okay. So we'll compare this simple interest and what's going on with our money, right? So let's say that we have the end of what year it is, and let's find out how much money we got in the bank. So at the end of 1 year, you've earned 5% of your $100, which is $5 in interest, but you still have the $100 in the bank, so you now have $105. Woohoo, took you an entire year to get $5. Well, you only put $100 in the bank, right? So, and these days, as of the date of this video, 5% interest is very hard to come by. So, but we're just using these as examples. Okay, so let's say that we go another year, we get another $5 because that's 5% of the original investment, and then we get another $5, we get another $5, we get another $5. So at the end of the 5 years, you've gotten $25 in interest, and you now have $125 in the bank. So how does this work out? Well, you start out with $100, and then what happens is you add your interest year by year by year. Okay, now this is the same exact amount of interest for 5 times, right? So where did this 5 come from? Oh, and this is 100. Okay. Well, this 5 came from taking 100 and multiplying by 5%, and this 5 came from the number of years, right? So this first $100 is called the principal. P stands for principal. This is called the interest rate, and 5 is the time, okay? So the formula for the interest amount on a simple interest loan is I equals PRT, principal times rate times time. Rate, of course, is a percentage, so you should change that to a decimal. So if you wanted the entire amount of money, you take your original principal and you'd add the interest to it, and you'd get $125. Okay, that's simple interest. So there's a different way to get interest with the same exact terms and time where you can make more money. And I'm going to explain how that works out. So we're still going to have to start out with $100, and we're still going to have a 5% interest rate, and we're still going to put the money in for 5 years, but this is going to be called something different. Okay, so let's explain what I mean by this. Let's say that at the end of the year, you get your 5% interest, so after year 1, you have $105. Okay, great. But now, since you have $105, what the bank decides to do, instead of giving you 5% of your original money, is now they give you 5% of what's at the end of the first year. So what we're going to do is we're going to take $105, we're going to take $100, we're going to add 5 to it, add 5%, and that's how much there is at the end of year 1, right? Well, at the end of year 2, we're going to take this amount of money and add it to 5% of this amount instead of 5% of the original amount. You can tell that you're going to make a little bit of extra money because you've made interest off of not just your original principal, but also last year's interest. So last year's interest goes into a new principal amount, and you have more money now, right? So I'm going to make this a little simpler for you. First off, we can take the 100 and factor this out, right? So we factor it out. What's left is one of those plus 5%. So this is 100 times 1.05. Or you could say that this amount is 105% of the original amount. Why 105%? Because you got 5% interest and 100% of the money that you invested. Nobody stole your money, right? Okay, so that's why it's 105%. It's all of your money and 5%. Well, if we did the next amount, okay, so this is all for year 1. Okay, if we did the next amount, we'd have that amount of money times another 105%. We'd have 100% of this plus 5% of this. That would be for year 2. And then for year 3, we'd have 105% of the previous year's amount. You can see what's happening, right? I keep repeatedly multiplying by 105%. So by the time I got to year 5, this is for year 3, by the time I got to year 5, it would be 100 times 105% raised to the 5th power. Okay, so this is an example of what we call an exponential function, exponentially increasing. And so I'll tell you how much money this actually turns out to be, and you can compare it to the amounts that we got previous in the video. So at year 2, instead of having $110, you have $110.25. The 25 cents here is 5% of $5. And then the next year you have $115.76, and then $121.55, and then $127.63. So you can see you're getting a little bit more money, because before it was $110, $115, $120, and $125. So we've earned an additional $2.63 because of how the interest was calculated. Okay, so this is called compound interest. And the compound interest formula says, okay, the amount at the end of 5 years is going to be your principal times 1 plus the interest rate raised to the time power. So here, the t is 5 years. The interest rate was 0.05, so this would be 1 plus 0.05, or 1.05, and this was $100. So that is a compound interest formula. Okay, what we can do is be really smart about how we compound the interest, and we can even do better than this. Let me explain what I'm talking about. So let's say that we don't want to wait an entire year before the bank gives us any money. Let's say something happens during that year and you need to take your money out. If you take it out before the end of the year, you will get 0 interest. You have to wait an entire year before getting interest payment, right? So what we'd like to do is we'd like for the bank to give us a little bit of interest along the way during the year. So let's say that we want to do this. Let's say that we want to take 5% per year, but we want to do this paid 5 times per year for 1 year. Let's just see what happens in the first year. So now we have our time. Sorry, I should not have made that so big because I want to work over here to the right. Now we have our first year split into 5 increments. So at year 0, we have $100. We just put the $100 in the bank. But what we're going to do is we're going to take that 1 year and divide it up into 5 little increments. So 0.2, 0.4, 0.6, 0.8, 1 year. And we want to see what's happening at the end of 1 year, right? So what would we do to figure out this first amount? Well, what we'd have to do is we'd have to take our 5% and split it up into 5 different chunks, 1% each. 5 divided by 5 is 1%. So we'd get 1% of our interest here, and then the next 1% here, and then the next 1% here, and then the next 1% here, and then finally we have a total of 5% paid throughout the year. But at least we didn't have to wait till the very end to get the interest. We got a little bit of it throughout the year, okay? So that makes more sense logistically, but you're going to find out that we're going to get more than $105 at the end of the first year by doing this. How does that work out? Well, right here, we're going to take our original interest payment and we're going to do 1.01. Now, why is that? Well, because in this first place right here, I get 1/5 of this interest rate. All right, so that's $101. But the next time, I'm not going to get $102, and here's the reason why. Because I get 101% of the previous amount, right? So what happens there is I have to do 100 times 1.01 squared, and I'm doing this in my web browser here. Oops. And I typed something in wrong, so hang on. All right, so now instead of having $102, we have $102 and a penny, which may not seem like much, but by the time we get down here, we're going to do 100 times 1.01 to the 5. Now, even though it's only 1 year, we've gotten 1, 2, 3, 4, 5 interest payments in that 1 year. So the exponent here is not the number of years, it's the number of times we got paid interest in that 1 year. Okay? So by doing this, by getting little bits of interest throughout the year, down here we have $105 and looks like 10 cents. So we got an extra 10 cents this way by doing it like that. Okay, so for that reason, the compound interest formula works like this. The amount that you get at the end of a certain time period is the principal times 1 plus r divided by n raised to the nt. So what's n? This n and this n is how many times you're getting paid throughout the year. So if we look at this again, the amount that we had there, and I'm doing the last one here, is the original principal plus 1 plus the original interest rate divided into 5 increments, and I'm sorry I put the parenthesis there wrong. And then the exponent is going to be 5 times 1, because it was 1 year, but we got 5 times per year, so we got 5 different interest payments throughout the year. So how does that work out? Well, I divide up my interest by 5 and I get 1% added, right? Well, 1 plus 0.1 is just 1.01, and then this was 5. And so now you can see why I did that. Okay, so this is the compound interest formula. And it's important to understand what all these little letters are for. P is the principal, R is the interest rate, make sure you write it as a decimal, N is the number of times per year that interest is compounded or paid, and then the exponent is the number of interest payments, and that's always a multiple of how many times per year you get paid times the number of years. So you might be wondering, hey, if I divide this up a huge number of times, let's say I want to get interest like 15 million times in the year, how much money can I make there, right? Turns out that there's a limit for that. So you can make N as big as you want. So let's do something a little bit better. Let's say that we did 5,000 times per year. Okay, so at the end of the 1 year, let's see what happens. Let's see if we can get, the bank to give us like $1 million, because we keep getting interest like every second or something like that, right? So we have our original interest, 1 plus 5% divided by 5,000, and we get 5,000 times 1, because it's only 1 year. So it turns out, if you put this in your calculator, the number's not very big. Let me type this in my calculator here. 1 plus 0.05 divided by 5,000 raised to the 5,000. Okay. This turns out to be $105.13. So you got 3 extra cents by doing it this way. Hey, it's 3 cents. And remember, this is only $100 for a year. So, if it were $10,000 for 30 years, that 3 cents would add up really quick, right? So how you compound the interest is really important. And if you make N infinitely large, okay, this formula turns out to be continuously compounded. Okay, that's if N is an infinitely big number, like infinitely big, bigger than anything you can possibly imagine. So what happens there is the amount is still to the principal times something, but it's multiplied by this thing called E. And the exponent now has, instead of N and T, it has R and T. And E is a number you can find on your calculator. It's about 2.718. Okay, so it turns out that 2.718 raised to the interest rate is the biggest amount that you can multiply your principal by every year. Okay, so if we did this for, we're $100 and we did e to the 0.05, why 0.05? Because that was our interest rate. And where's the 1? Well, anything times 1 is itself, right? All right, so it turns out that if you do 100 times e raised to the 0.05, you get $105.13. So it's a little, it's a super small decimal amount more than the 5,000 times per year was, but when you round off to dollars and cents, it's the same thing, right? It's the same thing. Okay, all right, so in summary, okay, we have 3 different interest formulas, right? We have simple interest, we have compound interest, which is compounded a certain number of times per year, and then we have continuous compounding. All right, so the simple interest is principal rate times time. And again, this is just the interest amount. If you want the amount, you have to take your interest and add to the original principal. So here the amount is the principal plus the interest, right? Here the amount is the principal, not plus the interest, but times 1 plus the interest rate divided up n times multiplied out nt times. However many times per year times the number of years. And then here, some people call this PERT, like the shampoo, but P-E to the RT. E is a number. Okay, E is about 2.718. You can find this on your calculator. It's usually next to the LN, and we'll talk more about LN next week. All right, so these are all examples of what we call, the last ones especially, these are examples of what we call exponential functions. So an exponential function is a kind of function like our compound interest, right? We have some amount multiplied by some base raised to some exponent. Before, this was the principal, this was 1 plus something, and this was nt, right? So this is an example of what we're talking about. Okay, it turns out that if b is smaller than 1 but bigger than 0, you get a graph that looks like this. Okay, this is called decay or decreasing. Okay, and this is 0a. That a is the y-intercept of the graph. If b is bigger than 1, you guessed it, it's increasing. Looks like this. So you might remember this from a previous math class you took, right? So this is increasing. I'll have to abbreviate because I ran out of room. Okay, so those are all examples of exponential equations. And so what's the domain? The domain is all real numbers. And the range is everything above the x-axis. So the range is from 0 to infinity. Don't count 0 because there's this thing here called an asymptote, so it will never touch 0. So if something decays exponentially, it never becomes 0, it just gets smaller and smaller and smaller. If your money is increasing exponentially, like in compound interest, you're getting more and more and more money, but you couldn't have started out with 0. If you started out with $0, then you'd have 0 money no matter what the interest rate was, right? So, okay. So remember, x is in the domain, y is in the range. All real numbers, only positive numbers, strictly positive numbers for the domain and range. All right, Alex will have lots more examples for you. We went through inverse functions earlier with just linear functions, so you'll have to deal with cubic functions. Next week we'll be able to invert the exponential function. So that's all for now. Have a great week.